So, in the previous clip we saw how we could solve the problem of the homogeneous linear time invariant ordinary differential equation, and we shall now see whether we can apply the same tricks and perhaps a couple more to take down the more complicated problem, the one that we are really interested in, namely the inhomogeneous differential equation, where you also have inputs on the right hand side. So, to recap what we are talking about, let me write out the differential equation that we are out to solve. It is nth derivative of x with respect to time plus a1 times nth derivative of n minus 1th derivative of x with respect to time, and so on and so forth, plus a n x is equal to b1 times mth derivative of u with respect to time, and so on up to bm u, and with these initial conditions x dot of 0 and so on, x n minus 1 of 0. So, in the previous clip we saw how this problem can be tackled when the right hand side has been set equal to 0, but having done that, that is not really our final target. So, we want to also see how we can solve the problem when the right hand side is not equal to 0, and whether we can draw any lessons from what we have gone through already for the homogeneous case. Now, if you stare at this equation for a minute, you will discover that it is not very easy to make inroads into this differential equation again, because u is firstly arbitrary, I can apply any arbitrary input, and the value of m is also m could be any integer. So, we have arbitrariness both in the value of m as well as in u, which makes it difficult for us to directly apply the lessons that we learnt in the case of the homogeneous differential equation for the non-homogeneous case. But I can certainly simplify the problem a little bit by exploiting the fact that we are dealing with linear systems. For example, on the right hand side I have m terms, b1 u mth derivative of u plus b2 m minus 1th derivative of u, and so on up to bm u of t. What I discover is that I do not really have to solve the differential equation for this entire sum of inputs, because we are dealing with linear systems. So, for instance, I can just solve the differential equation for the case when I have only u of t on the right hand side. Let me say x u of t is the solution when I have only u of t on the right hand side. In other words, if my differential equation were to look something like this, u of t, suppose the solution to that differential equation is x u of t, then if I were to have bm times u of t on the right hand side, the solution will be bm times xq of t. Now, if I have bm minus 1 times u dot of t as another extra input, then the solution to that would be bm minus 1 times xu dot of t, and so on and so forth. So that my final solution will be b1 times xu to the power m of t, not xu to the power m, xu differentiated m times, mth derivative of xu with respect to time. So, therefore, one does not really need to include all the inputs on the right hand side. One can just look at one of the inputs alone and then obtain the response, which I have called xu of t, and then differentiate the input m times and combine these derivatives in the right proportion, namely b1 times xu mth derivative of xu with respect to time plus b2 times m minus 1th derivative of xu with respect to time, and so on and so forth, all the way to bm times xu of t, and that is going to give me x of t. So, the problem that I really need to tackle is to obtain the solution for this differential equation plus a1 times n minus 1 of x with respect to time plus so on plus a n of x is equal to u of t. If I can take this down, then I know that I can take the more complicated case also down. Now how do we do this? Once again I want to remind you of the initial conditions. We have n initial conditions, x n minus 1, nth minus 1 derivative of x with respect to time at time t equal to 0. These are the n initial conditions. How do we solve this problem? Can we in any way draw inspiration from our attempt to solve the homogeneous problem? Well, if you look at it for some time, you discover that it is not really that easy, because u of t can be any general input and it is not 0. It is only when u of t is equal to 0 that we have the homogeneous case. So now we next ask ourselves, if we can find an input u of t that is rather close, that brings this system rather close to the system that we had for the homogeneous case. And it is in this context that we stumble upon the impulse input as a good candidate to have. What is an impulse input? You might have come across an impulse function in your undergraduate mathematics as a function of magnitude tending to infinity for a time that is tending to 0. So if I have the width of this function delta to be tending to 0 and its height to be tending to infinity in such a manner that the height times the width is a constant equal to 1, then this function we have called, you might have been exposed to as a delta function. This is also called as a Dirac delta function. However, this is a very restrictive definition for a function of this kind. A more general definition is a rather indirect one. So you call a function as a delta function, which we represent by using the symbol delta of t, as a function that gives us the value of any other function f at time t equal to 0 when we perform this particular operation. When we weigh down f of t with delta of t and integrate that over time, then we should get f of 0. Or more generally, if we multiply f of t with delta of t minus t naught and integrate it over time from minus infinity to infinity, then that should give me f of t naught. So you see here that there is no direct definition for a delta function, it is an indirect definition, in that a delta function is one which, when weighted with the integrand f of t and integrated between the limits minus infinity and infinity, gives me this particular function f of t 0. Hence a delta function is also called a generalized function or a distribution. So any function which when multiplied with f of t satisfies this particular equation here is a candidate delta function. Of course, you can easily verify that the Dirac delta function that we have drawn here easily satisfies this particular relationship, but there are also other functions that satisfy this relationship. For instance, if I were to define delta of t as limit n tends to infinity 1 by pi times t sin nt, if I graph it, it will look like a sinusoidal signal with decaying amplitude, and the frequency of the sinusoid is tended to infinity. I can show that this also represents a delta function. So there is no unique definition for a delta function, it is indirect. But for our case, for our engineering applications, the function that we looked at in the previous slide is namely a rectangle of unit area and of height that is tended to infinity and of width that is tended to 0, is an adequate definition. So height is 1 by delta and that is tended to infinity, and the width is delta that is tended to 0, so that the area is 1 unit. So this is an adequate definition for a delta function. Now let us apply a delta input on the right hand side of our system. Our system was x is equal to u, and u I have set as delta of t. Now why is this problem rather close to the homogeneous case? You see that in the case of a delta function, the input exists only for a very brief amount of time in the neighborhood of time t equal to 0. Before that there was no input, after that there is no input, which means that except for that small duration of time in the neighborhood of time t equal to 0, our system looks like a homogeneous system where you have no input on the right hand side. It is only in the neighborhood of time t equal to 0 is there any input, and all we need to look at is how the input in the neighborhood of time t equal to 0 changes our response. So once again I want to remind you that I have n initial conditions. However, I already know how to solve the problem when I have n initial conditions and no input on the right hand side. So let us now simplify the problem by assuming that initially all these initial conditions are 0. In other words, before application of the input, in other words at time t equal to minus delta by 2, or I shall also call it as 0 minus. Okay. At time t equal to 0 minus, all these initial conditions are 0, and then there is this storm, namely this huge input of infinite, nearly infinite magnitude that is applied on the system for a very brief infinitesimally small duration of time, and then that changes the initial conditions in some way, and then once again you have the homogeneous case, because the input has gone to 0. On the right hand side of this equation you would have 0, and you would have to solve the problem for the new set of initial conditions that come about because of application of this delta input. Now how do we find that new set of initial conditions? We find it by matching the singularities on the right hand side and on the left hand side of the differential equation. We notice that on the right hand side we have delta of t, and therefore we should have a matching delta of t on the left hand side. Now the question is, where can this impulse input reside on the left hand side? Can it be in the term x? If it is in the term x, you see that you also have x dot, x double dot, and so on and so forth on the left hand side, which means that if x of t is proportional to delta, then we would have x dot proportional to delta dot and so on and so forth, but we do not have terms related to delta dot, delta double dot up to delta to the power n on the right hand side. So clearly the delta input cannot reside in x of t. How can it reside in x dot of t? Similarly, if you have delta function in x dot, in other words if I were to set x dot equal to some constant times delta of t, you will discover that x double dot will have delta dot and so on and so forth, which are not represented on the right hand side. So you can continue this argument until you discover that none of the lower order derivatives of x can contain the delta function, because if they do, then there will be a higher derivative of the delta function on the left hand side, which will not be balanced by a corresponding term on the right hand side. Therefore we would have to have the nth derivative of x alone to be a delta function. Now what this implies is that the nth derivative of x is essentially the derivative of n minus 1th derivative of x with respect to time, and that is equal to a delta function. Now if I were to integrate this expression between the limits minus delta by 2 to plus delta by 2, then I would have between the time limits of minus delta by 2 to plus delta by 2, then I would have this to be delta of t dt between the limits minus delta by 2 to plus delta by 2. Now between the limits minus delta by 2 to plus delta by 2, we see that integral delta of t dt represents the area under this curve, and this we know by definition is equal to 1, because the height of this delta function is 1 by delta and its width is delta. So what we discover therefore is that on the left hand side what I would get is the n minus 1th derivative of x at time t equal to 0 plus minus n minus 1th derivative of x at time t equal to 0 minus is equal to 1. Now we know from our initial conditions that the n minus 1 derivative of x at time t equal to 0 minus was equal to 0, which implies that the n minus 1 derivative of x with respect to time at time t equal to 0 plus has to be equal to 1. So now we see the effect of a delta function. Immediately after the delta function has been applied, the delta function changes the initial condition of the system. All the other initial conditions remain unchanged. It changes the initial condition of only the n minus 1th derivative of x by 1 unit. Of course, if I had b m times delta of t, then it would have changed the initial condition by b m. Just by matching the singularities I can get that. So now we have obtained the response of the system to an impulse input, and this response is called the impulse response. Let us now obtain the impulse response for a particular numerical example. So let us take once again the differential equation that we considered, x double dot plus 3x dot plus 2x equal to 0 is equal to u of t, and I am setting x of 0 minus equal to x dot of 0 minus equal to 0. To obtain the impulse response, I set the right hand side u of t equal to delta of t, and by matching the singularities what I would discover is that x dot of 0 plus would be equal to 1 and x of 0 plus will be equal to 0. Now at time t equal to 0 plus I have these new initial conditions, and my delta of t is such a function that it ceases to exist beyond time t equal to 0 plus, or t equal to 0 plus is the same as t equal to plus delta by 2. Therefore we have a homogeneous differential equation, namely x double dot plus 3x dot plus 2x equal to 0 for t greater than plus delta by 2, and with the initial conditions x dot of 0 plus, or in other words x dot of delta by 2 is equal to 1 and x of delta by 2 is equal to 0, where delta is a very small quantity. Now what is the solution to this differential equation? We can employ the same tricks. Now it is a homogeneous differential equation with a certain given set of initial conditions. This is something that we have already seen, and we can solve it and get the solution to be x of t equal to e power minus t minus e power minus 2t. And since this is a response to a specific kind of input, namely an impulse input, this is given a specific symbol g of t, and it is called the impulse response. Impulse response. So now we have made some progress in that we have managed to solve the inhomogeneous differential equation, not for any general input u of t, but for one specific input, namely a delta function. How do we go from here? We notice that our delta function by definition allows us to connect the input u applied at a time t to its previous history. By definition, therefore, u of t is equal to delta of t minus tau u of tau d tau, where the limits of integration are from 0 to, or from minus infinity to plus infinity. This is just the definition of the delta function. However, I can choose to apply my inputs to the system at any specific time, and therefore for reasons of convenience I shall choose to apply it at time t equal to 0, so that my lower limit of the integral becomes 0. Now this is an integral, and an integral to me as an engineer is a glorified sum. Okay, it is an infinite sum. I can therefore write it approximately as, I can break it up, I can look at d tau as some elemental increment of time delta tau, and write the input as u of k times delta tau, and the impulse input as delta of t minus k times delta tau. So, in the limit that k tends to infinity, this sum essentially converges to this particular integral. So, as an engineer, therefore, I can view this integral as a sum of different inputs u applied at different instants in time as decided by this delta function. Now, as an engineer, I can consider the input u of t as a train of impulses of magnitude u of k times delta tau times delta tau. Now, let me just graph this particular expression. So, if I for the case when k equal to 1, I would have a delta function at centered at delta tau and of height and of area given by u times delta tau times delta tau, and plus for the case when k equal to 2, I would have a delta function centered at 2 delta tau of area equal to u of 2 delta tau times delta tau, and so on and so forth. So, the summation of all these inputs is the actual input u of t. Now, we see that we are dealing with a linear system, and since we are dealing with a linear system, the response to a summation of inputs is a summation of the response to individual inputs. The response x of t is equal to the summation of the responses to each of the individual inputs. So, k equal to 0 to infinity, the response to one input delta of t minus k times delta tau is the impulse response centered at k times delta tau, which is g of t minus k times delta tau, and the magnitude of the response is decided by the magnitude of the input, namely u of k times delta tau times delta tau. Therefore, my response x of t can be written as a summation of the responses to each of these individual inputs, u of delta tau times delta tau, an impulse function of that magnitude applied at time t equal to delta tau, plus an impulse function at time t equal to 2 delta tau of magnitude u of 2 times delta tau, and so on and so forth, and that is what is represented by this equation. And in the limit delta tau tends to 0, this would reduce to the integral 0 to infinity u of tau g of t minus tau d tau, and thus we have succeeded in obtaining the response to any general input u of t. Let us now illustrate this by means of a numerical example. For the same system that we considered before, namely x double dot plus 3x dot plus 2x is equal to u of t, x of 0 minus is equal to x dot of 0 minus equal to 0. Let us try to obtain the response to the input u of t is equal to 1 for t greater than or equal to 0 and 0 for t less than 0. So, this is called the Heaviside step. So, it changes its value from 0 to 1 at time t equal to 0. To do this, we first have to obtain the impulse response of the system, which we did a few minutes back. We know that the impulse response g of t is e power minus t minus e power minus 2t. So, the response to the general input, in this case u of t equal to 1 when t greater than or equal to 0 and 0 when t is less than or equal to 0, is given by x of t equal to integral 0 to infinity g of t minus tau u of tau d tau. Here I want to make one more modification to the limits of this integral. We notice that we are dealing with physical systems, and our physical systems cannot respond to inputs that have not been applied yet. They can only respond to inputs that have been applied in the past or at the instant of application. and that in turn means that when tau is greater than t, g of t minus tau has to be equal to 0. So, such a system is called a causal system, and all physical systems are causal, which means that x of t has to be evaluated only till time t, and beyond time t g of t minus tau will go to 0, and we do not have to worry about the magnitude of the integral. So, this is the integral that we have to evaluate, and this we shall do by first substituting the value of g of t. So, g of t minus tau is e power minus t minus tau minus e power minus 2 times t minus tau, and we multiplied with u of tau, which is a constant of magnitude 1, and we integrate this between the limits 0 to t. If we do the integration, what we will discover is that this integral is equal to half minus e power minus t minus plus e power minus 2t by 2. So, to summarize, we have obtained the solution to the differential equation nth derivative of x with respect to time plus a1 times n minus 1 derivative of x with respect to time, so on and so forth, plus a n x is equal to u with the n initial conditions x of 0, x dot of 0, x n minus 1 derivative of 0. Of course, when we solved this equation, we assumed that the initial conditions were 0, but if you have some non-zero initial conditions, the response of the system would be the sum of the responses to the initial conditions plus the response to the particular input u. Now, if you want to obtain the solution to the more general case, where on the right hand side you have, instead of u, you have b1 mth derivative of u with respect to time and so on and so forth up to bmu, all you need to do is, having obtained the solution xu of t that we did just some minutes back, we can represent the response to the general input given by this expression as x of t equal to bm xu of t plus bm minus 1 x dot u of t and so on up to b1 x m u of t. What I hope you have appreciated from the material that we have discussed over the last 2 or 3 clips is that we have managed to solve the differential equation where the degree of the differential equation with respect to x is n and the degree with respect to u is m, where both n and m are arbitrary and u is any arbitrary input, and we have managed to do it by first starting with the homogeneous differential equation, looking at how the solution appears for the most simple case, namely when n is equal to 1, and then from that, using a combination of intuition and some special inputs such as the delta function, we have managed to solve the most general case, namely when you have this term being equal to this term and for some n set of initial conditions.